So from the first bit, from example 19, right, they've established this little property here that if you've got z cubed equals 1, these are our zeros, 1 w squared, where w is cis 2 pi on 3. And we can extend that to actually to say for any power of z, so z to the n equals 1, the roots would be 1 w squared, w3, all the way up to wn take 1. So if it was z to the 6 equals 1, then this would become z to the 5, w to the 5. Okay, and then we say where w is cis 2 pi on n. So applying that, we can then say when we've got z plus 3 cubed equals 1, we apply this. So we're going to say, well, therefore z plus 3, the roots will be 1 w squared, where w equals 2 pi on 3. But we don't want z plus 3, we just want z. So to get rid of the plus 3, all right, we know we're going to take 3, and so w is cis 2 pi over 3, and we'll take 3. Now w squared, right, so w squared, and I should write that in there, but I'm just not leaving myself too much room, but that is there, and from de Moivre's theorem, we know that that becomes 4 pi on 3. Okay, so my other root would then be cis 4 pi on 3 minus 3. So 1 take 3, we've got minus 2 as one of our roots. And you know, you could leave it as this and cis 2 pi, but I just want to show you how it all relates, right? So when we've got our cis 2 pi over 3 minus 3, let's use our calculator to suss what that is. So 1, put your angle there, 2 pi over 3, take 3, okay? So we get that that is minus 7 over 2 plus root 3 on 2i. Now, we'll check this second one, but we shouldn't even need to use the calculator because it is the pair of this root, right? It's going to be the conjugate. So it's going to be minus 7 over 2 minus root 3 over 2i. But let's go and just double check that. So we'll go up and we will replace the 2 with 4, okay? And you can see, bang, it is correct. So that's what the question was just asking you for. It didn't actually say to do any of this stuff. It was just asking you to leave it as probably there in terms of W, but we just want to go on and so you understand what is going on. Now, what does this actually mean? Well, if these are my roots, doesn't that mean that I can factorize it? Right, so this would end up being that using these roots, I would have a factor of z plus 2 from minus 2. And then with these two complex conjugate roots, I can use sum and product, right, to work that out. Now the sum of minus 7 over 2 times 2, that would be minus, so the sum would be minus 7. Okay, so that becomes plus 7. And the product, and you can check this on your calculator if you really want to, but the product would be 13. Right, 7 over 2, so 49 over 4 plus 3 over 4. Yep, 13, so we get plus 13. Okay, so what we're saying here is that from these roots you get this factored form, right? And so that actually means that this is equal to z plus 3 cubed take 1. So if the question had asked you, how do I factorize, or can you factorize that using the nth roots of unity? Well, you can. If you want to check, does that actually work? You can quickly use synthetic multiplication, or you can do normal multiplication. So we've got 14, 1 times 2 is 2, put your 0 there. We've got 13, 7 and 1, add that up. 26, 27, 9 and 1. So this is saying if we expanded, we would get z cubed plus 9z squared plus 27z, plus 26. Okay, now to expand this chap, let's change the colour for that one. All right, to expand this guy, we're going to use my best mate, Pascal. Okay, so remember 1, 3, 3, 1. So that would be 1z cubed plus, oops, what happened to my cubed, plus 3 times 3z squared plus, and then that would be plus 3 times 3 squared z plus 1 times 3 cubed, and then we've got to take the 1. And if you work that out, you will find that you get exactly the same as that. So that's sort of why we do this.